is a multidisciplinary work thanks to the collaboration with geochemistry, biologists, and physicians, etc. Foraminifera are a very fascinating, at least for me, single-celled eukaryotic microorganism. They living in all marine environments, but also sometimes in fresh water environment, and can be planktonic and benthic. And they first occurrence very deep in time, in the geological time, in the Precambrian probably, with a very simple organic, naked organic shells. And then during the evolution, they experimented a very different kind of biomineralization. You can see agglutinated, high magnesium calcite, aragonite, low magnesium calcite, and also during Cenozoic silicate, and etc. So, but in this presentation, I will focus especially in bilamellar perforate calcitic test, low magnesium calcite. Why? Because this kind of biocalcification is likely at the origin of the evolutionary success of this foraminifera group. Is extremely high, diversified, and abundant in the today ocean. And also this kind of biocalcification allowed probably the evolution from a benthic life mode to planktonic life mode. And then I would like to stress that the carbonate produced by this calcareous foraminifera account for 25% of the planet production. So with an evident impact in the global carbon cycle and climate regulation. This foraminifera, this perforate calcitic foraminifera, they are extremely used in paleoceanography and in paleoclimate study. So they are really true actors of global climatic change, global cycle regulation, but also the accumulation of their shale in the sea bottom sediments are also a very important archive. Oops, no, the next. I remember you that this calcite foraminifera are the composition, the isotope composition, and the element trace composition of this calcareous foraminifera are the most used proxy in the paleoclimatic and paleoceanographic study. Here, for example, 65 million years of climatic change records, thanks to the isotope composition of benthic foraminifera, so are very useful for this reconstruction in a long time, at a short time scale, but at also long time scale, thanks of the continuous record of this foraminifera. Oops, sorry. But we saw in the discussion with Anders Mebom for corals and other biocalcifiers, also for the foraminifera, for sure, there is the problem of the biological unpacked the use of foraminifera as a paleoenvironmental archive is complicated by biological process. So so how calcium and minor trace elements like, for example, magnesium and strontium are transported from the seawater to the site of calcification. This is a key question to understand the biological impact on element incorporation and isotope fractionation. The cellular mechanism which foraminifera employ to precipitate calcite must be identified. No general consensus on this mechanism exists. Normally, actually, the recent most popular mechanism invoked is a bulk seawater endocytosis as the main mechanism for the ion supply. Another possible is a ion supply to the mineralization based on membrane ion transporters. So, how I told you before, endocytosis of the seawater is now, in the present, considered as principal mechanism in foraminifera biocalcification. Here you can see a very spectacular image. This is the cell of Amphistagina. The red are algal symbiont. So this is the internal cell. This is the seawater that are labeling. And you see the cell membrane invagination and trapped the seawater. This invagination formed some special vesicle inside the cell. And this special vesicle are supposed to be an internal calcium pool, that one side, and the other, this vesicle could control the concentration, the carbonate concentration, with a supposed mechanism through a pH increased control. So the bicarbonate are pushed towards a conversion to carbonate. Then this vesicle are transported in a supposed site of biocalcification that its name primary organic members, recently is more named as a primary organic sheet. So these vesicles are transported on these sites where there is the nucleation and then there is the nucleation of calcification. So it's a very important. I come back. Excuse me. Oops. So. I told you about this primary organic sheet. So a key question is, what is this primary organic sheet? Maybe a key to understand the mechanism of biomineralization of this foraminifera, as it's better understand the composition and the role of this primary organic sheet. So this was the question, the problematic of our study. And what we do to answer to this question, we take ammonia as model. Ammonia is one of the most used foraminifera for biocalcification study. Here you see a living cell of living ammonia foraminifera, and with you can see the shell inside the cell, the shell is covered by what is named ectoplasm that form a sort of rhizopodial network around, very complex. So in this picture, you can see the chamber formation of ammonia. And this foraminifera, we can say, grow in the discrete steps of new chamber addition. So each chamber represents a step of growing. Here we can see that when the chamber forms, there is a retraction of a pseudopodial network, you see. So the pseudopod delimited a space that take the template of the shape of a chamber, you can see. And in this delimited space, the calcification happened, and take some hours, and 9 hours was observed to have the final formation of the chambers. But here there is still ammonia shell. This is a SEM micrograph image. What we did, I broken the last chambers, and so we can see in this piece a detail of a structure of the wall of the last chamber. So here you can see an inner organic layer that covered the inner part of the shell. This is the outer organic layer that covers the outside part of the shell. Here, this thin line represents the primary organic sheet or primary organic membrane that represent the site of calcification, and in opposite direction we have it's supposed to be the calcification, the inner organic calcitic layer and organic, the calcitic inorganic layer and the outer calcitic layer. This is a sort of simplified picture to show then when a chamber is forming, the outer calcitic layer go to cover all the previous chambers. So the old chamber are thicker, how you say, respect of the last chamber, and this shell in totally is a multi-layer shell with a calcitic layer alternating with the organic layer. So, but look more closely to this primary organic sheet. To do this, we use a focus ion beam technique, and to prelay the very thin samples, and this technique allowed us to have a very nice section that cross the anterior wall. Here we can see the pore wall, the primary organic membrane. And this technique was very useful because for a first time we can get at the same time the calcite and the organic layer. In the normal technique, often there are dissolution of calcareous, the calcitic part, or vice versa, but never both were observed together. So when Sylvain Bernard showed me this STEM image, I was very surprised because how you say, this is the primary organic sheet or membrane. How you say it's not at all a continuous homogeneous sheet. I was very surprised. You can see there are irregular, almost two irregular, very tiny organic layers. And inside is sandwiched a calcite part. It's no more bilamellar studied, but three-lamellar structure. And we were very happy of this synchrotron X-ray absorption result. And Sylvain Bernard showed me this Xanes spectrum of a primary organic membrane, so of the in situ measure of this very tiny organic layer. I take attention of a scale. This is a 160 nanometer scale. And this Xanes spectrum pattern is typical of lipids. So, if this is the site of calcification, this fingerprint of a lipid suppose us that this primary organic sheet is really a primary organic membrane, and probably the rest of a cell membrane, some remains of a cell membrane that are any more functional, but was trapped after the biocalcification process. So this is a very fundamental application because ion supply to the mineralization are probably based on membrane ion transporters. So another nice evidence came from the proteomic study that I conducted in collaboration with Anna Sabatini, Arul, Maria, and Sofia, and other colleagues. And we get some, for the first time, we get some peptide sequence in the shell organic lining of this giant benthic foraminifera, Schlumbergella floresiana. And we get a lot of sequence of a peptide, novel sequences, so unknown, probably came from unknown protein unique for foraminifera. But what we get, very interesting, some peptide pattern that are close related to calcium and hydrogen transporting ATPase protein. So this is discoveries go in the science of the evidence that we saw before. Another nice study against the existence of an internal calcium pool is this nice experience in vitro using a labeled water marked with the isotope calcium 44. So in this experience, the foraminifera were growing in this labeled calcium 44, and you can see the last chamber marked in yellow. This means an increased ratio of calcio 44 respect to calcio 40, and also you can see the last chamber marked, and also the outer calcitic layer that cover the entire old chamber. And then for another experience, the foraminifera was in water with this 44 label. Then the foraminifera was get out and put in a normal seawater. And how you see the last chamber are not labeled with the 44 calcium. So this means this evidence go against of a calcium pool. Don't know if so for conclusion, the site of calcification in perforate calcitic foraminifera primary organic membrane, I think we can call primary organic membrane, is likely the cell membrane itself. Ion transmembrane transport plays probably a very important role in the biocalcification of this foraminifera. Transmembrane transport is generally characterized by strong difference in selectivity for different elements. For example, the discrimination of a typical calcium channel against magnesium is much stronger than against strontium, explaining probably the low values of magnesium-calcium ratio in this foraminifera. Seawater vacuolization, endocytosis, and the dissolved inorganic carbon intracellular reservoir cannot be totally ruled out, and they could also contribute to the biocalcification, but the interplay of this mechanism are also due to better understand. Sorry for my English, and thank you for the attention.